All right. I wasn't really sure what sort of level of experience to expect. Usually there's a few experienced people and a few newbies. So I hope there's something in this talk for everybody. I think what I want you to walk away with is that it's important to evaluate the performance of a machine learning model on a separate validation data set that's not used for training. I also want you to walk away with the idea that randomly splitting your data into train and validation sets is not always a safe plan. And then sort of the more sophisticated part of the talk is going to be some tricks that I've used to automate the process of identifying similar images in a data set. And let's see. So yeah, presentation plus Kaggle notebook. If you want to have the notebook open, then you don't have to squint at my tiny screen share. You can run a copy of the Kaggle notebook without needing an account on Kaggle. And the notebook has some suggested exercises. So if you want to sort of think about things a bit more carefully, then maybe the exercises have a sort of range of abilities, but there's some that are easier than others if you wanted to give them a go. Alrighty, so let's see if I can move this out of my, okay, that's better. So this talk is everything except the model. So usually when you do machine learning, the model gets all the attention and the spotlight, but a lot of the success of a model has actually got nothing to do with the algorithm. It's to do with the data and how you evaluate whether the model is working properly. So when you start off with a problem, you ask questions like, what is the problem? Are we solving the right problem? What metric is appropriate? What is the existing solution to this problem and how good is it? And I would probably add to this questions like, how are you going to determine what sort of strategy or feedback mechanism do we have for evaluating whether the predictions that this tool is making is correct? So these are the sorts of questions you sit down before you maybe even think about getting your data. So we move on to the orange text where you ask questions like, do the training images look like what we expect to see in production? Are the labels mostly correct? Are there images that could cause problems, like things that are blurry or duplicates? And then the meat and potatoes of what this talk is going to be on, the red text, how should the training and validation sets be split? And what are potential sources of leaks? So we try to answer the orange and the red questions by exploring the data. So what do I mean by this model validation process? So the idea is you take some of your data, usually 80%, and you train on that data, and then you score the algorithm on the remaining validation set, the 20% left over. And there's really three goals of validation. You want to be able to decide when to stop training. So the goal is to stop training at the point where the model generalizes well to both the training data and the unseen validation data. So this little, I guess, image from Wikipedia, the black line is a pretty good fit because it gets most of the red circles on one side and most of the blue circles on the other side. The green line is overfit because while it's getting all the blue circles on one side of the line and all the red circles on the other side of the line, if you had other additional data, you may find that the pattern is not, you're going to get more items wrong in the validation set than you would if you'd stopped fitting earlier. So one of the other goals of the validation process is to have some sort of system to decide whether your improvements to your model are really improving the model, or to be able to select the best model. And usually you also want to have some idea of some way to estimate what the upper bound is on how well the model will perform in your production data. And usually whatever you train before production, that's going to be a little bit very often quite optimistic compared to what you get in production, because usually there's differences between the production data and your training data. So why wouldn't you just use a random process for splitting your data into a training set and a validation set? So one way to look at this is to go and actually look at the data for this data set. And the first thing that I notice is that there's like a whole bunch of images of aluminum cans, but they're all the same aluminum can. And this could be dangerous. If you have a picture of an aluminum, let's say your training data had only one aluminum can in your data set, Now, when you go to production, you have many other different aluminum cans. It's going to be a lot harder for your algorithm to extrapolate from the aluminum can, the only aluminum can that was in the training data, to the exotic aluminum cans that are in production data. So bad training validation splits can cause you to overestimate how well your model's performing. Okay, so let's do it. This is a little exercise. Actually, who's on the Slack here? I can't see, but is it? Let's see. Maybe Matt can sort of DJ the chat. If anybody's not on the Slack, go and join the Slack, because this would be a good exercise to think about for a partner. So the challenge is you have data that can a data set that consists of bottles and cans. So the bottles are these bottle-like shapes, and the cans are the can-like shapes. And the goal is you want to train an algorithm to predict whether an item is a can or a bottle. And here's two possible splits. There's split 1 and split 2. And so I would like you to think about which validation set will it be harder for the algorithm to extrapolate to. Is it harder to extrapolate from train 1 to validation 1? Or is it harder to extrapolate from train 2 to validation 2?
Kiri, what do you mean by getting people on Slack? How does
just so that if you want to have like a discussion about something, or like let's say you're new and you don't understand what the heck I've said, but you don't want to interrupt me because everybody else seems to understand. If you have a buddy who's on the Slack or the chat who also doesn't understand what the heck's going on, then that probably means that you should interrupt me and get me to explain myself better.
I've seen this talk before, and I remember I was confused last time I saw this talk, and I had to admit I'm confused again. So can we go
okay,
over?
Let's go think about this a bit more carefully. So let's look at training set 1. There's a red bottle and there's a green bottle.
Right.
And there's a gray bottle, and then there's also a gray can, a red can, and a green can. And in the validation set, there's a green bottle that's rotated a bit differently from the green bottle that you have in the training set. There's also a green can, a red bottle, a gray can, a red can, and a gray bottle. So let's look at the second training validation split. So in training set 2, there's a red bottle and a rotated red bottle and a rotated gray bottle, and then three different rotations of the same green can. Now validation set 2 has got 3 green bottles, different rotations, a red can, and 2 gray cans. So I guess the question is training set more similar to validation? Is training set 1 more similar to validation set 1, or is training set 2 more similar to validation set 2? Does anybody have any thoughts?
1 is more similar, and 2 is more dissimilar.
Yeah.
So the 2 might turn out to be a better model.
Yeah, that's exactly the point. So every bottle that's in training set 1 shows up in validation set 1 but rotated, whereas in training set 2 there's no green bottle at all in training set 2, but there is a green bottle in validation set 2. So now the algorithm is going to have to learn how to extrapolate from like Coke bottles to Sprite bottles in order to label the bottles in validation set 2 correctly. So what we want to be able to do is to build a conservative training validation split. So you want to make going from the training set to the validation set the hardest task possible. And also I wanted to add, if anybody wants to interrupt me anytime, I'm totally happy. And actually I would prefer to be interrupted, because it's otherwise really hard for me to tell like if people are like zoning out or lost or have just sort of given up. So I would really prefer, if you don't understand something, just interrupt me. I'm not bothered. I would very much rather you speak up.
I got a quick question. Does this assume that you've got small data sets?
This works on any size data set.
Okay. But
Yeah.
if you got like a very large data set, then won't the probability of having these clusters go down? Or?
I think it depends on the sort of data that you have. So if you have cans and bottles, maybe at some point you do start to have, if you have a really huge data set, you do start to have every possible, you have a Sprite can, you have a Coke can, you have a root beer can, you have a Iron Brew can. you really have every possible kind of packaging that has ever been manufactured in your training set. So you're right. If you have a bigger data set, you do tend to mitigate this problem of extrapolating, but it is still something that it's important to think about, I think.
I think another reason why this is really good to think about is like from your earlier example with that Coke can on the plaid background, you had, if you can imagine just a random split, you would have a Coke can on a plaid background in your training set, you have a Coke can on a slightly rotated, a slightly different in your validation set. And maybe the model is learning some other pattern that you don't really want it to learn, right? Like maybe it's just learning that certain plaid pattern. It's saying that is a Coke bottle. Then we really don't know by looking at the validation score whether the model has actually learned something significant or just kind of some
got
random
distracted
pattern.
by something in the background.
Right.
All right. Okay. So in this case, here's my sample production data set where I have a blue bottle and a long purple can. All right. So the other thing I wanted to think about is how to make the fold splits for cross-validation. So my preferred method, offered with no theoretical justification or guarantees, is to make 6 folds. And so let's look at the training model iteration 0. I'm going to train on 4 folds. I'm going to train on fold 0, 1, 2, and 4. And then I'm going to do early stopping on fold 3, which just means I'm going to check to see when I'm training on fold 1, 2, 3, and 4. And then on fold 3, I'm going to check to see if the loss starts increasing. If it does start increasing, I'm going to stop training. And then I can go and evaluate the score on fold 5. And I'm going to do this for a couple different splits. So in iteration 1, then I'm going to train on fold 1, 2, 3, and 5, early stop on 4, and then evaluate on 0. And what I actually really like about this method is it gives you some idea of the amount of variation in some metric like your accuracy or like whatever metric you're trying to optimize for. You get some sense of how noisy your results are. And
can I interrupt? Can you explain that early stopping again?
So when you're training a deep neural network, you don't know when you should stop training. If you train for too long, what you're going to do is you're going to overfit. Remember that plot that I showed with the yes, this one, the overfitting plot. So if you train just enough, you're going to be on the black line. That's what you want. But if you train too much, you end up the algorithm starts to like memorize the data rather than generalize to a pattern. And so you end up with this green line, which is it's separating the red and blue circles, but it's not it's not learning a pattern that will allow you to extrapolate to novel data. Does that make sense?
Sorry, when you decide when to stop, you're looking at the loss function, or you're looking at accuracy, or what are you looking at?
Yeah, you could look at whatever you like. Usually, you look at the loss function. So if you train as you're training, you're trying to minimize the loss on the training data, but at the same time, then you have this additional early stopping data set, which you check what the loss is. And if you find that the loss on the early stopping data set stops going down and starts increasing again, then you know you should stop training, and you know where the best model is, where the model that generalizes the best to the early stopping data. And then because you use that early stopping data set to select the point where you're going to stop, you actually want to go and have the validation set left over so you can estimate the performance of the algorithm. Is that clear? Okay. So now that we have this sort of fold split philosophy, the problem becomes how can we split the data into folds such that the algorithm is forced to learn to extrapolate rather than just interpolating amongst similar images, which is the easier task. And how can we split the training data into folds such that it's maximally challenging to extrapolate to the validation fold?
Quick question about the folds. Does it make sense to randomize the contents of the fold at each, iteration or epoch?
So as you're training, so you will go through what's called an epoch, and in that epoch, you'll have looked at all of the training data that you have available, and it's in the red folds. And when you're training, what the algorithm actually does is it shuffles the order of the items. So the very first group, you might look at 64 items at a time, but the next epoch that you do, you'll look at the first run through, you'll look at a different 64 items. So you're always looking at a batch made of like 64 items, but those items will be grouped together differently every time.
Okay, that makes sense.
Okay. Let's see. So cross-validation fold construction. So one of the goals of data exploration is to identify features that are likely to have values in production data that didn't occur in the training data. We want to identify features that we think may not be distributed in the same way in production data. Or maybe we want to look for correlations present in the training data, which we don't expect to occur in production data. And the fold splits should reflect the kinds of extrapolation that we expect the algorithm is going to have to do going from the training data to the production of real data. Okay, so let's go fire up Kaggle and look at the this data set page here. Okay, sorry, I have the little zoom tab which is covering up part of my screen, and then I have to move it so I can get to the tab here. Okay, so you know what? I'm actually just going to see if I can put this link in as well here. Okay. Actually, Matt, can you help me with this? Because I don't think I have enough bandwidth to do this. And
Yeah, what do you want to do?
I'm going to send you a message here, and then can you share that with everybody else? This is just linked to the Kaggle data set. All right. So I guess if you've never looked at Kaggle before, they're famous for running competitions, but they've also they've started awarding points for contributing data sets. And well, this has been interesting because people have contributed a lot of data, and some of it's really good and some of it's not so great. And I think the interesting thing about this that you can learn just by looking at this is that there are only 2 notebooks for this data, and one of them is mine. And the other one is automatically generated. So that's, I think, already telling you that this data set might not be the world's most useful data set. But let's see, what else can we see here? So there's a little little verbal description. And he says here, this data set contains parts of another data set collected by Gary Fung and Mindy Yang, and then he collected some of his own data as well. All right, so what else can we see from the sort of the Kaggle interface? So they've got this little data explorer over here, and they've got 2 directories, YOLO images and raw images. So let's open up raw images. There's 4 folders: aluminum can, glass, HDPEM, and PET. So there's 4 classes in this data set, and the images are basically just dropped into the folder with the label that they belong to. Now let's see, for the YOLO images, oh gosh, why is this so slow? Well, the YOLO images, it turns out to be exactly the same thing as raw images, but they've included additional text files with bounding boxes around the parts of the images that contain a picture of, or contain like the can or the bottle. Let's fire up. Let's look at the, oh yeah, so here's the YOLO images. And you can, let's see, if you double click, oh yeah, so you double click YOLO images. Now you can preview all of the elements in this directory. So there's a can and then the associated text file. So for this, we're actually just going to look at the raw images directory. And this Coke can that's oh so memorable from the slide. Oh my goodness, so many pictures of this Coke can. And then, okay, now there's a green can on a slightly different backdrop. So already just by doing a visual inspection of this image data, we have some sense of where things are going to go wrong, because you see we've got a whole bunch of pictures of the same can, and that happened more than once. And I guess the other thing that's interesting is that we know there's at least 2 different backgrounds. So there's the plaid background and there's this sort of wood paneling background as well. Okay, so now that we've looked at this data set information, that we can fire up the Kaggle notebook. And I guess I want to draw your attention over here to the right where there's the input folder. And what I've done is I've added the drinking waste classification data set. So the data set that we were just looking at, it's over here. And then I've created an additional drinking waste classification data set here, where I've got a file called metadata CSV and a file called vector.pickle. And I just created these files because there's some processing that's done in the script that's really time consuming, and I didn't want to make you wait while we did all that processing. So I've output the output of that processing over here. Okay, so let's do the fun part of reading what's going on in this notebook. So we start off by just by loading the data. And yeah, there's some annoyingly formatted file names that I parsed. And then we can kind of get a sense of just what we did visually. We can look at what directories do we have, what is the file structure. We can do that with Python code. And oh yeah, get an idea of how many images are in each class here too. So I printed out in each directory how many files are there in the directory. So you've got 1,000 to 1,500 files in each directory. And okay, now we can also take a look at some of the sample images here too. Oh yes, this can looking very familiar now. Okay, so the first sort of exciting thing that we can do is try to pull out some metadata associated with the images. So usually when you have like your phone camera, or really any camera now, you take a picture and there's a bunch of metadata associated with that. And if you use the Python image library, PIL, Python image library, then you can get to the image metadata with this get exif command. And oh, yep, I do not need to edit that. And okay, so I picked an image 0. I ran get exif on it, and it spits out a whole bunch of numbers. So does anybody see anything that looks familiar in this whole pile of numbers here? You can volunteer the information.
The time string there?
Yeah, there's a timestamp here. Well spotted. Anything else that you could understand?
It's not an Android.
And it's not an Android.
Shot on an iPhone.
Shot on an iPhone, yes. Anything else here? Let's see. What about this suspicious looking W here? And there's an N over here.
So location?
Yeah, so GPS coordinates. Yeah, so there's a bunch of juicy stuff in here that they just told you. And you know what? I was actually kind of horrified when I noticed the GPS coordinates were there because let me actually go back to the talk here. Oh, I missed a bunch of stuff I was going to talk about. Okay, I'll go back and do that. Yeah, because
the capital W and the lowercase b and the numbers, I thought maybe it was the embedded model.
Oh, I don't know what the B stands for actually. But the N and the W are telling you north and west for GPS coordinates. So what this guy just told us is where the photos were taken, which is probably where he lives. And it turns out it's a dormitory in London. So as soon as I noticed that, then I sent him a message and said, did you know that you just announced your address to the entire planet? And he's like, oh, I don't live there anymore. And I'm like, okay, good. I'm so relieved because I don't have to pretend now that I didn't notice that you have the GPS coordinates in your data. Yeah, so this metadata. You know what? I'm going to back up and look at some of the discussion I had from the data exploration too, because that's sort of interesting. So one of the things I said before you start building a model is you try to think about whether the data you have is actually going to help you solve the task that you want to solve. And in this data set, we've got all these pictures of individual cans or bottles on a background. But if you were trying to actually build something to use like at a recycling factory, probably what you'd be looking at is like a conveyor belt full of cans and bottles. And so that's problematic already. So you want to, if you're going to create an artificial data set, you want to make something that's going to mimic the production environment as close as possible. And the other thing I did not like about this data set, if you have a plastic bottle, there's two types of plastic involved with this bottle. There's the body of the bottle that's made of one kind of plastic, and then the lid is made of a different kind of plastic. If it turns out if you only use one kind of plastic, the seal doesn't, the seal at the lid isn't very good. So that's why they use two different kinds of plastic. So having an algorithm that labels one kind of plastic for an image that actually contains two kinds of plastic may also not be the goal that you're trying to achieve. And then, so let's say you want an algorithm that identifies trash. And this is a really interesting problem because trash is something that depends a lot on context. So is the left image of trash? No, it's not trash. But the right image is probably trash because we know from the context that on a beach, you're not expecting to see a can of Coke and it's not trash. On a beach, if you see an empty can of Coke, then it's probably trash. So you can have the exact same bottle, but the context is telling you something about the label. Okay, let's go back to the let's go back to the metadata here. Okay, so we pulled up this metadata out of this image, and what I'm going to do is I have a little bit of the script that's going to extract the camera info, so the whether it's an apple or not, the timestamp, the GPS coords, and actually the image height and width. I'm just going to put that into a pandas data frame, which is like for the non-data people, this is like basically SQL, but for me, I guess. Yeah, it's basically a database tool. Okay, so we can work out how many images there are for each class, and also how many unique cameras were used to generate the data for each class. So this is where things start to get a little interesting. So I've got aluminum cam or the label, so aluminum cam, glass, two types of plastic, and then the camera, and I have counted the total number of images which are aluminum can and iPhone, or aluminum can and NAN. And what you notice already right away is that like 95% of the aluminum can images were taken with the iPhone, whereas, whereas only 2/3 of the glass bottle images were taken with the iPhone. So right away, without even knowing anything about the picture, you could already make a really simple model that can, just based on the camera, guess at what's in the picture, which is not what we want. We can also look at just how the image height and width are distributed for each class. So here I've broken it down: aluminum can with 384 and width 306 or 683, and then all of the NAN cameras have width 384, and all of the iPhone images have width 363. So you can already tell just from like the camera and the aspect ratio what images or what object is going to be in the picture. So let's see. So all of these are the same aspect rate. Let's see if there's another set of images where the width is not 384, whether it's 512. So here's, for the pet images, there's some images where instead of taking the photo in landscape mode, the camera was flipped around and it was taken in portrait mode. And so just knowing that allows you to make a perfect prediction about which item you have just by knowing the aspect ratio of the camera.
A quick question about, so you just mentioned earlier that just by knowing the type of camera, it already kind of gives away what class it falls under, whatever we're trying to classify. Is that because metadata is also used in training, or is
we're not going to use the metadata explicitly in training, but you could sit down and build a model. And actually, the thing that would use that data, but you don't want it to use that data because that data is not relevant to the task that you want to solve. In production, you could have somebody go out with an Android phone, and now the metadata is totally useless.
Right.
One of the other things you have to be careful about with the aspect ratios when you're training a image classification task. Sometimes what happens is that you pad the parts of the image that are, so if you have a portrait image and you have a landscape image in the same batch, what you do is you pad the part of the image that's missing. So now all of the images are the same size. And if you you could just pad it with zeros. And when you do that padding, what you're actually doing is you're telling the algorithm what the aspect ratio of that photo is.
Oh, because it knows if it's portrait or
because now you have a way to tell that. Now you're explicitly telling the algorithm whether it's portrait or landscape. And so you have to think of one way to get around it is by cropping the image, but you still have to be a bit careful that you're giving away information to the algorithm that you don't want the algorithm to use. Okay, so let's see. Let's take a look at the timestamp data. What I did here is I converted the timestamp from Unix time to a time delta in days. And so the useful information here is now we find out how many days elapsed between the first image in the data set and the last image in the data set. And there was 137 days between the first image in the data set and the last image in the data set, which is, I mean, that's commitment. That's like a 4-month period that this guy was running around taking pictures of stuff with his phone. Respect. All right, so now we've had a gander at the metadata. What we'd like to do is to use a pre-trained neural network as an unsupervised algorithm to generate vectors representing the images. And I think for this, I'm just gonna hop back to the slides here. Okay, so this is the sort of standard picture of what is a convolutional neural network doing. And so the low levels of the network are constructing filters that find edges, and the higher layers in the neural network can do things like find faces. And then by the end of the network, you can do things like say, this is a picture of Sarah. So at each step in this, as data sort of propagates up to the right in this algorithm, you get a more abstract representation of what is in the image. And this representation is actually just a bunch of numbers. And if you can roll them out into a flat row, and you can call that a vector. So what we're actually going to do is we're going to take this algorithm and we're going to chop off part of it. We're going to chop it off maybe around here. We'll definitely chop off this last dense layer. We can chop off maybe a couple of the final convolutional layers. And then we're just going to have the algorithm spit out some numbers, and we're going to change that into a little row of numbers and use that vector to represent the content of the image. Is that clear to everybody? Because that's a bit of a leap. Okay, so the detail. Oh, sorry.
Could you go back to that previous picture? So are you saying you're starting with image on the left? You're going to put it through these various layers, and then you're stopping just before you get to the vector part? Or?
Yes, I'm gonna stop a bit early. You could stop here. You can actually experiment a little bit with where you stop. But yeah, just pick something fairly close to the end. And then what's good with the numbers that are going to come out there, that's just a representation of the content of the image.
So basically you're converting each of those images into those set of numbers from that last sort of convolutional layer?
Yeah.
Okay.
Yeah. Yeah. And I mean, the reason this kind of works is that you have this pre-trained neural network that that's trained on ImageNet. So with ImageNet, you've looked at a whole bunch of cats, dogs, trees, chairs, cars, bicycles, you name it. It's looked at it. So as long as your data is sort of like in that sort of visual, like if you're looking at like cytology data or astronomical data, there's going to be less overlap between the astronomy or cytology domain with what's in ImageNet. And you might find that you have to change like where in the network you chop things off, or you may find that just doesn't work as well as you may find if you start with ImageNet and you train for an astronomy task, you are basically learning a completely new domain.
So in that first phase, you're not doing any training. You're just putting it through pre-training.
No training. Yeah, that's
okay.
right.
Fine.
Yeah.
Okay, thanks.
Yeah, and then so that's the reason why it's kind of an unsupervised method, because you've just taken this pre-trained model that you trained on a maybe somewhat unrelated task, and now you're exploiting the fact that it's learned to do things like find edges or like find different kinds of textures. You're exploiting that to construct a representation of the images that you're interested in. Okay, and that's probably the most exciting part of the talk. So I really want to make sure that people are satisfied that they understand that. This is totally insane. Like you would take an algorithm that you trained on like the ImageNet task for 1,000 different classes of objects, and then you just chop off part of it, and then now you have an algorithm that can be useful at looking for patterns in data that it's never seen before. That's pretty amazing.
Kiri, in terms of where you cut it off, if you're cutting it off where there's still those like dimensions where it's kind of like that grid, and then I suppose you're just flattening it.
Yeah.
Is that right?
Yeah.
Do you lose some information about that? Because I would assume that there's still like some positional information captured.
Yeah. So there is still positional information encoded here, but I think that's okay. I mean, if you have a picture of like a landscape, then what's at the bottom is when you enroll something in a vector, what's at the bottom will always be in the same position in the vector in all landscape images. So
plus, presumably, you're going to take these embeddings and put a dense layer or two afterwards, and the dense layer has the ability to look at all the positions. And
you know what? We're not going to do any supervised learning at all. This is totally everything unsupervised. But you're right, you could do that.
Right, but what my concern
basically
is that if you have like a can in the top left of the image and that exact same can with the same background and everything in the bottom right of the image, maybe they would be slightly different in that point, but like a little bit later down, once the network has already flattened it, maybe that would positional information would be captured.
There's more at the lower end of the algorithm, the lower layers. There's more positional information encoded in like where they're like if something's in the top right hand corner, it's going to activate the neurons in the top right of this convolutional mapping. But by the time you get to the last few layers of the image, that information is all kind of more blurred out. So you have less positional information and more abstract information about what's going on in this image, what kind of textures are in this image, what kind of objects are in this image. All right.
David, did you have a comment? I think you got cut off. No?
Oh, no, it's fine. I was just saying that it's essentially identical to an embedding.
Yep, exactly. Yep.
Yeah.
Yeah, an embedding is a representation of an object in an abstract high-dimensional space, and that's basically what we're building. Okay, so the nitty-gritty part. Now, if we want to get rid of the last few layers of this model in PyTorch, there's a slightly annoying problem where if you can't just drop layer 4. You actually have to go in and replace layer 4 with an identity matrix or identity operation, I guess. So an identity operation that takes the input and it just spits out the output. And it's not easy to just remove layer 4 completely from this code, but you can redefine layer 4 as an identity operation. So what I'm going to do, this is like ResNet 18. I'm going to keep the first 3 layers, and I'm going to chop off layer 4 and then this average pooling, flatten, and the fully connected or the dense layers at the end. Yeah, okay, so let's go back to the notebook. So we want to use this pre-trained algorithm to generate the vectors so we can do some clustering. And the idea is that the vector representing similar images, so you have 2 similar images, the vectors representing those images are going to be more similar to each other. They're going to be closer in space than the vectors representing images that are different from each other. So what we're going to do is we're going to construct the vectors for the images, and then we're actually going to go in and compute the distances between those vectors. Okay, first part, we need to compute the vectors. So we're going to fire up PyTorch, load a pre-trained model. I've got ResNet 18 here. Downloading. And I started with ResNet 18. I define an identity layer, and then I replace the 4th layer with the identity layer. And then I do an average pooling operation, and then replace the fully connected layer with an identity operation. And let's see. Yeah, so now this is what PyTorch spits out for my my model. And let's see. So we have to normalize the input Okay, now we can write the data set class. So this is basically just saying I'm going to have some mechanism for going and fetching each of the images that I want to compute the vector for. And let's just check to make sure that what's coming out of that is the correct size. We can also use check to see that it looks like it's sort of sane. This is more or less with 3 channels for the color, and then this image is 512 by 384, so that looks pretty good. And now we want to check that it goes to the model correctly. So I use extract the 4,000th item from the data set, and then pass the image value through the model. And what comes out is something what comes out is this vector that's describing this image. I'm going to look at the size of the vector. It's 1 by 256. So I've taken the image that's, 384 by 512 pixels, and I've made a representation of that image that is a vector that's got 256 elements in it. Okay, so now we're ready to do the labor-intensive part of computing all the vectors describing each image. So this is the slow part of the code. And yeah, if you want to, if you're interested in an exercise to learn a little bit with, then trying to figure out how to speed this up is an interesting problem, or trying to figure out what part of this operation is slow is interesting. Okay, and so now that we've, I've used, I've already generated the vectors and I put them in this vector.pickle file. So when you run this code, you don't actually have to generate all the vectors yourself. But I'm just now reading them from the vector.pickle file. And what's something that's good to do is to check the histogram of some of the values in some of the image vectors. And basically what we want to see is that we didn't end up with the model mapping all of the images to a vector representation that's like all 72 or all 0. And if we do that, that probably means that if the algorithm constructed is basically the same vector representation for all the images, that's telling you either that you screwed up the normalization of the images, or that the pre-trained model and the image data that you want to manipulate, that they're actually very different. So if you took like all astronomy images, which were like black, and show them to a pre-trained model that was trained on the ImageNet data, then indeed, if you show pictures that are almost all black to ImageNet, it's probably going to represent them all as the same vector. So this, looking at the values in the vector gives you some idea of whether the pre-trained model is actually going to be giving you useful information or helping you to distinguish between images in a useful way. And okay, so I just plotted this histogram so I could see that that's not all the same number. That sounds good. Okay, so now we have the next problem, which is how to efficiently calculate the distance between image vectors. And I'm going to switch back to the slides here. All right, so we have this, I guess it's an array of image vectors. So each row in this image vector array is a vector that's representing an image. So if we want to compare the difference between the first image, the blue row, and I guess this is the 0th, 1st, 2nd, and the 3rd image, the red row, then what you would want to do if you're working in Euclidean space is just take vector 1 minus vector 2, subtract them and square them and sum them up. And so I want to emphasize that there's a slow way to do this, which is with a for loop. And anytime you are writing code in PyTorch and you see for loops, that usually means that you are missing an opportunity to speed this code up by using tensor operations. So there's, the fast method is I guess I've written it out below, using the torch matrix multiplication mechanism. So I'm doing this operation where I'm calculating the magnitude of the difference between vector A minus vector B, which is the same thing as vector A dot A minus 2A dot B plus B dot B. And there's a smart way to do this. And yeah, this is my plug for taking in a linear algebra course. If this math is unfamiliar, then taking linear algebra can help you appreciate how to do things efficiently with linear algebra operations. All right, let's see, I think we can go back to the slides or to the notebook here. So The next bit is just the efficient implementation of how to calculate the distance between all the vectors in your data set. So there was like 4,800 images in the data set. What we want to do is we want to calculate the distance between the vector representing each image and the vector representing every other image in the data set. So what we're going to do is we're going to build up 4,800 by 4,800 pairwise comparisons of every image to every other image. And so I said we could do this as the Euclidean distance, but you could also use, there's a correlation metric, which is actually related to the distance, or you could use like the square root of the distance as well. So all of these are defined here if you want to play around with them. Is there a question? Okay. Okay, so the goal when we started with was you wanted to be able to identify similar images so we could group them together in the same fold. So what does this 4,800 by 4,800 image look like? All right, so on the y-axis, we've got the correlation matrix, or I guess in this case, it's probably the distance matrix for the image vectors. And you can see it's symmetric. So there's this line down the middle here. And everything that's above the line is mirrored below the line. And what's interesting is that right now it's just ordered by the file name, but we can already start to see that there's clumps of similar images. So the image similarity is over here on this heat map bar. So if their images are very similar, then the distance between the images is 0, and the pixel comparing image I to image J, that's red. But if the images are very dissimilar, then the pixel's green. So we can already see just from using the order of the files in the data set that there's clumps of images together that are similar.
Sorry, one question. Why isn't it red right down the diagonal?
Probably it is, but it's probably because the image is so large that it's missing the resolution to see that. But yeah, I would expect that it's red all the way down the diagonal.
I think the fact that we're seeing little clusters in this already tells us that there's a data leak in the file names.
Well, probably the file names just come from the order that the images were taken in, right? So he probably took picture 1, then he took picture 2, and then he took picture 3.
Yeah.
So like the examples I'll refer back to here is like the cans that you had that were all taken in a row.
Yep, exactly. Yeah. So this is basically what we're seeing here with that there's clumps of similar images. That's basically what we expected from having manually inspected the images on the Kaggle data set exploration.
And I'm sure you must have said this somewhere along the way, but how many different classes are there that we're trying to identify? 4. Okay.
Yeah.
I have a question there. The blues are large distances.
Yep.
And they are saying that there are some groups, at least 2 groups of different images that are very different to the others, isn't it?
Okay, so let's go look here. So these images here, this would be like image 1,400 through 1,550. Those images are all very similar to each other. Where there's blue lines here, so there's a whole row here that's blue, and there's another whole row here that's kind of bluish as well. So it looks like there was kind of a couple of one-offs where he maybe went to a different place and took pictures of something that wasn't on his bedspread or wasn't on his shirt or wasn't on his dorm room floor. And maybe that's what's causing these images to be different from a lot different from the other images.
But it is useful for the purpose of what you talk in the very beginning, no?
So that's the idea now that we've constructed this measure of how different the images are from each other. Now we can go in and try to sort the images so that groups of similar images are all put together. So that's the next step. Let's see. Oh, okay. But let's first improve this plot. So Bruce was actually just asking. There are 4 different classes. I've actually plotted the class label over here on this left-hand side. So now I wasn't smart enough to put the label on it, but I think this is probably just in the order. So that was can, glass, and then the 2 types of plastic at the end. And you can basically see here too that there's like a sharp boundary when you switch from plastic 1 to plastic 2, that there's like a new cluster of images here. So that's pretty gratifying. Oh yeah, and I guess the only other comment I wanted to hear, this was ordered by the file name here too. Okay, so how are we going to group these clusters together? So my weapon of choice is fast cluster. I know there's other packages, like I think there's the FAISS package that's made by Facebook. It's also doing a similar thing, clustering together vectors that represent things. And they probably have some smarter tricks up their sleeve, but this is just what I had, so I've used it. And this doesn't work too badly either, fast cluster. I didn't write this. I poached it from somebody else who did a nice job on these routines. But it's what it's going to do is it's going to, when you pass this correlation matrix into the compute serial matrix, what it's going to do is it's going to spit out this ordering vector, and it's going to tell you what order it arranged the images in so that the similar images are placed together. And I guess I want to add that there's more than one method to decide whether image vectors are similarity. So this is what I'm passing here with this parameter, or the method is ward. There's a bunch of different possible strategies to use, and you can actually kind of tinker with this as well. This is something else you can play on.
Another question. That fast cluster, what do you have to specify the number of clusters, or what sort of parameters do you have to specify for it?
No, so that's the other excellent thing about fast cluster is it's not actually going to formulate clusters. It's only going to order the clusters. So this is, and the reason that I like this is that now I don't want to have to impose my ideas about how many clusters there should be. I just want it to pick an order that seems okay. And
order based on what? The
image similarity. So what I'm going to do is I'm going to show you, maybe I'll just show you a flashback here to this is the original data, ordered by the file name. And you can see there's already clumps, but let's go down here and look at the image data ordered by fast cluster. And look at this. Fast cluster really knows how to find clusters, because now it's grouped together a bunch of images that are all similar. So you can see there's all along the diagonal, all the red pixels where you have similar images are together along the diagonal. And I've continued to put the class label along the left-hand side here. So you can actually see that there continue to be clumps where the label is the same, but it's also mixed it up a little bit. And so probably that's telling us is that there are a bunch of images of different items that were taken on the same background.
Just one more question about like the inputs. Like you mentioned, there's like different methods of choosing similarity. Do you know what ward stands for? Is it something distance?
I have no idea. I would have to look it up in it's all in the documentation.
Fair enough.
Yeah. I think when I did put this together in September, I went in and looked at it more carefully, and then I forgot. But I mean, that's my life. I look something up and then I forget it, and then I look it up again. So
I think that's everyone's life.
All right. Okay, so the cool thing is about once we have, if you have a small enough data set, you could actually just generate this overlap or this ordering. And then you can just go right ahead and split it up, if you like, into 6 more or less equally sized clusters for your. So each of these clusters is now going to be a fold in your training and validation process. And I guess the thing I want to say is there's not really any theoretical guarantee that a particular split is going to produce the maximally challenging training validation split. So it's fine just to experiment and see what happens. Usually there's like there's like one cluster where you kind of like end up putting all the things that didn't really fit into other clusters. So that's sort of what's happening down here. And then there's this one cluster here that's a little bit bigger. This cluster is a bit on the smaller side. That's not ideal, but it's not, a factor of 2 is not the end of the world. All right, let's go back to this notebook. All right, so we have this other metadata here. Let's play around a little bit with this other metadata. So the subsequent plot here I've made with the image width group. Okay, what the hell does that mean? So I've got over here on the color bar, the image width. And so this color, the color is now telling you over here, it's telling you about the image width, and in the main part of the plot, it's telling you about the similarity of the images. So this color bar over here is doing double duty. Now, the interesting thing is that you can see that there's actually this a bunch of images here which have the same width, the red corresponding to the red, 384 pixels wide. And those were the images that came from either the iPhone or the NAN camera. I can't remember which it was, but the algorithm, without knowing anything about the image dimension, it actually managed to cluster those images all together here, which is pretty mind-blowing. And then let's see, yeah, there are a bunch of other chunks where there are images with the same width that the algorithm has put together. Yeah, especially through here because it's all basically the same here. And there's a bit more variety up here to the top of the plot. Okay, we can also fiddle with the GPS coordinates and look, we can calculate we can do a shitty calculation of the distance between, the physical distance between the image locations that the photos were taken at. And I've done this the wrong way because it's fast, but I want you to all know that it's the wrong way and that I know it's the wrong way, you know it's the wrong way. And if you ever have to calculate the distance between 2 points on the globe, don't use this method because it only works when the points are super close together. But I made this little plot here with the latitude. It's the seconds only part of the latitude and the seconds only part of the longitude. And guess what? There's like 3 little clumps where this guy was taking pictures of. Probably one of these is his dorm room, maybe one is his lab, and the other is like the store or something like that. So you kind of get a sense of how much this guy moved around while he was building this data set. So we want to I made a shitty way to calculate the distance between the images. And so what happens now if we plot the ordered, let's see, this is the image label, and then what I've got over here is the physical distance between each of the images. And I plotted the log of the physical distance between the location of photo I and photo J. So whoever said before that the diagonal should be all red. Now it should be all white because the log of 0 is not a number. So that's why we're seeing 0 white along the diagonal. So this is just the original order from the file names in the data set. And I plotted over here the color corresponding to the image class. But what's kind of mind-blowing is that you can see there's a clump of images here which are all taken super close together. Another clump of images over here which are also taken super close together. This clump down here which is taken super close together. So that was the image order and the location data are related. And okay, so now what if we run this through the cluster? We reorder the image so that it's ordered by the clustering algorithm. Now it puts all of these images that are taken close to where the physical location for the image is close together. It puts them all together here. So this is actually these are the images where the GPS metadata was missing, the white images here in this segment. And then there's another bunch of images here which are taken far place from each other, or far place from the other images, but close to each other. So that's informative as well. And the clustering algorithm found that without knowing anything about the GPS metadata, which is pretty mind-blowing. Okay, so now we can try using k-means to generate 6 clusters because we know explicitly that we want to end up with 6 clusters because we want 6 folds for our training and validation process. So I've just whipped out k-means. What I was hoping for here was that k-means would find, oops, I did not want to do that. I was hoping that k-means would find that k-means would find 6 more or less evenly sized clusters so that we could just plug that in for our folds. All right, this is likely going to take a minute or two to rejigger itself here. Maybe I can see if anybody has any questions or comments while I'm working on this.
Question. So you did that fast cluster that found the clusters in this page you're showing.
Mm-hmm.
And then why are you using k-means again to do additional clustering?
I just want to show you that it's going to find somewhat similar clusters.
Okay.
Okay, let's see. Run all, yeah. So maybe you actually, so one of the other things that we want to use the clustering algorithm to learn to do is to identify when there's similar images that are of the same object. So the thing is, if we have a training set where there's 2 images of this can, and then there's 4 images of this red bottle, now the bottle counts for twice as many, it counts for twice as much when you're evaluating the loss as the can does. And that's kind of unfair. So especially if you had like 50 pictures of one can and 1 picture of another can, now all of a sudden you're really biasing the data, you're biasing the algorithm towards focusing on the can that you have 50 pictures. So if you had a way to go in and try to figure out which images were of the same object, that would be super useful because it helps you weight, as you're training your supervised model, it would help you weight the images that are of the same object. It would help you weight them correctly. And so that we can go in and use the fast cluster trick again with a little, and give the algorithm a little bit more information as well. All right, let's see if this has got fired back up here. Okay, oh, they're almost there. So yeah, identifying multiple images of the same object. Let's see. Okay, this is more or less where I wanted to get to. Okay, this is pretty eye-popping colors here. What did I do to generate this plot? So what I did was so each of these, this is just ordered by the file name again. So each of the images in the first clump, they belong to the same class. This is the aluminum can class, and then there's another clump here for the glass bottle class. And what I did to generate this plot was I took the image vector distances from the previous analysis, and then I said, I'm going to take whatever distance is the largest in this plot, and then I'm going to add that distance to vector pairs that belong to different classes. So something that's comparing a bottle to a can to a bottle. So if you're comparing a can to a bottle, you're in this region here. I said, okay, I'm going to add a bunch of extra distance to that. So I'm going to this is basically me telling the algorithm that an image pair that's in this region here, they're definitely far apart. Don't want you to consider that they're close together at all. So once I've done this, basically I've constructed a new distance matrix that I can feed to my clustering algorithm. And I use the agglomerative clustering tool for this. And again, there's some inputs like you can control the methodology with whether it's Ward or not. And you can set the number of clusters. But I just leave the number of clusters as 1, and then I can tune the distance threshold to determine how big or how small the clusters get. And this is something you actually kind of have to play around with. So what we want to do is want to set the distance threshold so that as what we see is that the algorithm is selecting images of the same object for the same cluster, but not including images that are of different objects in those clusters. And this is not really an exact science. It's just sort of a half-assed way to get you part of the way there. Let's see. All right, so I guess what I've done here is I've looked to see, so I'm not setting the cluster size. I'm just varying this distance parameter, and I can look to see what is the number of images in the largest cluster, and the algorithm came up with 8. And then I also asked to print out the image indices for the largest cluster. And so what I'm looking for here is that they're close together, because I know that they are ordered, the file names are ordered in time. So what I was expecting to see is some indexes that are really close together, and that does actually seem to be the case here. And then the proof of the pudding is doing some visual inspection. So you want to see, let's look at all the items in this large cluster and see if they're of the same objects. Okay, so here's this wine bottle on this wooden floor background. And what's interesting to me is the back of the bottle is visible in these first three images. but it's the front of the bottle that's visible in these subsequent images. But it does appear to be the same bottle. So what we've done now, we've made this tool that can cluster the image vectors together to, first of all, help us create a good training validation split among 6 different folds, and to second of all, to identify groups of images which are probably containing the same object. So I think for the rest of the talk, I'm just going to go back to the slides here. So one idea that's sort of interesting to think about is, could you automate this process of doing fold splits? And so the idea is here that models are good at interpolating, but bad at extrapolating. So if you have a whole bunch of, if your training data is a whole bunch of items in this cluster, and maybe a whole bunch of items from this cluster, what you'd like to do is you'd like to know, okay, in my test data, I'm probably going to have to extrapolate to a novel cluster. So the question is there a way that you could infer just by looking at the training data, whether you're in the situation where you would have to, in production, extrapolate to a novel cluster? So another way to think of that, oops. Any comments? All right. This is a little bit subtle, so tell me if it's not quite sunk in. Another way to state this question is, do we have to have some external knowledge about whether making predictions on production data will involve extrapolating to novel values of a feature? So we've already sort of thought about this problem, whereas if you have a data set with 2 kinds of cameras, do you expect to have other kinds of cameras to exist in the production? And we know about cameras, there's definitely more than 2 types of cameras in the world, so we definitely expect that we would have to extrapolate to novel kinds of cameras. What about if you are considering patient data for patients from different hospitals? Do you need to extrapolate to novel hospitals in the test data or in production? And this is less clear because maybe you're building a model for like one health authority in BC, and you have a fixed number of hospitals that aren't changing. Maybe you only care that the algorithm can interpolate amongst the hospitals that are there. But maybe you want to be able to extrapolate to different hospitals. That's not clear. And now if you think about a problem where you have a Borgle, which is something that I don't even know what it is. So if you have 2 kinds of Borgles, would you expect to see a 3rd kind of Borgle in production? Without knowing anything about what a Borgle is, you don't know whether there's only 2 kinds of Borgles in the universe, or whether there's like tens of thousands of different kinds of Borgles in the universe. So I think that my conclusion is that from looking at the training data, you can't actually have an automatic or like a clever machine or a clever information theoretical way to tell whether you can expect to have to extrapolate to a novel value of a feature in production. But this is an interesting idea to think about, because I think it's one of the mistakes that people make the most often. So if you could try to automate this, that would probably save people a lot of grief. So yeah, there's not really a way to automate for an abstract, automate splitting on a particular feature into different folds for an abstract piece of data. But the usual suspects for images for candidates to split on are things like the image dimensions, the camera type, the GPS latitude, longitude in the metadata, and especially the aspect ratio of the images. So what you really end up having to do is to manually go through the features and ask, is the algorithm going to have to extrapolate to novel features in production, yes or no? And if it's going to have to extrapolate to novel features in production, then you can consider using this feature as a value to split your training and your training folds on. If you're not sure whether the production data is going to require extrapolation, then you can also just make the split the conservative one. Okay, so one of the interesting things about academic research is it doesn't really place much value on tasks where the training validation split is important, but Kaggle does place a lot of value on this process. And there's been a couple of kind of famous competitions that Kaggle's run where doing a really careful train validation split has been really important. So I've listed a few of them here. And Matt will probably remember the fisheries monitoring competition.
Yeah, I was nodding. Yes.
All right, and oh, look at this. I can't believe this is 2 minutes to 8 o'clock, and I'm on my beer slide already. So what I want you to take out from this talk is that getting a data set and implementing a feedback mechanism to label it can be the most expensive and time-consuming part of doing machine learning. It takes more time than doing the actual machine learning sometimes. Randomly splitting data into train and validation sets can be dangerous. Sometimes you want to do something more conservative so you have a better estimate of how your algorithm is going to perform. And the technical part of the talk was demonstrating that you can use pre-trained neural networks as unsupervised models to generate vectors describing images, and that you can go and compute the distance between the vectors describing different images and use those distances to group the similar images together. And I guess my last point is I think everybody should try to drink beverages out of reusable glass containers and not out of disposable plastic ones. All right, does anybody have any questions or comments? I guess actually I want to just thank the guy who put together this data set. Even though I kind of pooped on it, I recognize it's a lot of hard work to make the data set, and I appreciate that work.
Thanks,
So I have a
Kiri.
really dumb question.
Yeah, sure. I bet it's not dumb.
Yeah, it is. So I was thinking back to, like, I don't know if you can get back to the slide where you're showing the fast cluster stuff, or before and after you did fast cluster those. I guess particularly the one before, and you have the class labels on the side.
Yeah.
Like, I was thinking about this. It seems like the fast clustering thing is going to do the exact opposite of what you want, because you're using it to scramble your classes.
Yeah, but that's okay, because also really.
Yeah, go ahead.
You want to end up with, so maybe the first comment is you want to end up with each class being represented when you're training. You don't want to end up with, if the images are so different that the algorithm is able to, the unsupervised algorithm is able to split them up. Like, let's say you apply this to like ImageNet, the ImageNet data, then it would actually, the algorithm was trained on, it would actually probably do a very effective job of splitting up all of the images by the class. But I guess it's useful in this situation because the images don't correspond, the class information doesn't correspond perfectly to the information or the classes that are in the image or the ResNet 18 task.
So you're actually sort of counting on this embedding to not be an accurate, like, you don't expect the clusters in the embedding to actually represent the classes.
I think it depends on like how close your images are to the ImageNet data, whether you expect that or not. But also because in this data set, the bottles themselves were a small portion of the image, but there's some other stuff going on in the background. So this is telling you something about the background as well.
Right. Okay. But I mean, you could also, I won't belabor the point. Okay, I'll belabor it just a little bit. So you could hope that, suppose you wanted to use these embeddings that you get from the pre-trained model as the basis for a clustering algorithm that identifies the classes correctly. And suppose that worked really, really well, then wouldn't this technique fail, because it would tend to put all images from one class into one of your folds?
Yeah. So that's one thing I think I did put that in there, but I should probably belabor it, is that you want to make sure that your the folds, that each fold ends up with representation from all of the classes in it.
Yeah. Okay.
And I think the other thing, and maybe I should say, is I think this technique probably works better on data sets where there is like the background. You want to be able to sort of, there may be sort of like information in the background that you don't want the algorithm to learn to use. Like the fishing boat problem, there was like the training data that you saw in Kaggle was like 8 fishing boats. And then in the test data, there was 4 fishing boats that you'd never seen before. So, and the fish was only a very tiny portion of that image. It was mostly a picture of the fishing boat. And then there was a little tiny fish somewhere in that picture. And so you didn't what you didn't want the algorithm to do was to learn to say, oh, this is Sloop John B, so it's got to be tuna.
Indeed, yes.
Yeah, but I think that's subtle. I think that was a great question. Any other comments?
Quick question, Kiri. Thanks for the presentation. I'm curious, when you're deciding where to lop off your network, did you explore the depth of that, or you've had a couple applications before and you have a good idea of how deep to cut it off, or what was your motivation or decision there?
Yeah, I think I've always just played around with it a little bit. Again, it depends on how much the data resembles the data that the pre-trained network was trained on. But I usually find that lopping off the last few convolutional layers is useful too. That if you lop off the last few convolutional layers, you're actually preserving some of the spatial image, the spatial data in the image as well.
Great, thanks.
Kiri, sorry, go ahead.
I have a question. So what's a good approach in a situation where one of your classes or some of your classes have very low representation and diversity? So maybe there's only a few examples and maybe all of those examples are very similar. Is it better to just split them up so that there's
as soon as you do that, though, you're going to overestimate. I think at that point, it becomes more a problem of it's less a problem of how do I do the training validation split and more of a problem of how do I go and get more data for this class.
Right.
Do you have any thoughts about how this will work with data augmentation? For example, in the case of images, just how it will change the distances in that latent space? Or do you have any thoughts about it?
If you chop off the neural network at the very end, you're at that point most of the spatial information has probably been thrown away. So the vector representation of the image is probably going to be the same if you rotate it versus if you don't rotate it. If you chop the neural network off at a lower layer, you're preserving more of the spatial information, and then you may start to see differences between the representations of the image and then the rotation of that image.
And same will happen with the, let's say, noise, adding noise. It will be filtered by the first layers?
If you added random Gaussian noise, I don't think that would make a very big difference. Yeah. I think maybe the other thing I want to address is that it doesn't actually make a lot of sense because we don't really need to augment the images, because all we wanted to do was to have the goal of this process was to have some mechanism that would help us find similar images. And so if you augment an image, then you already know that the image is going to be similar to what you've augmented. So that doesn't actually help you in any way.
Yeah, no, but I was thinking in terms of what you will find in production, because you were talking about different models of cameras, and maybe one of those is you can kind of try to fake the noise that another camera.
So I think actually what you want to do with this analysis is you want to prevent the situation where the algorithm is using the information about which camera took the picture to make the prediction. And by doing a good training validation split, you're stopping the algorithm from using that information. That's really the goal here.
Okay. Thank you.
Yeah. I think that's really subtle, but really important. Let's see. I was just trying to think if there's anything that I could point you to read that would help. Yeah, if I come up with a suggestion, I'll put it in the Slack.
So the procedure here is intended to get a better balance on your sample data compared to random sampling. Do you have any examples to kind of show what the benefit would be for your model extrapolation, or?
Okay, so literally that slide with all the Kaggle competitions on it, if you didn't do a good job of doing your training validation set, you did not do, there was just no way to do well at these competitions, because
Sure.
All of them, in all of these competitions, the test data was sampled from different populations than the training data was. And there was usually fairly obvious, doing some data exploration, that there were like population clusters in the Africa soil competition. The cervical cancer competition is super interesting too, because in this competition, it was medical imagery, but taken with conventional phone cameras. And it turned out that you could tell, every doctor had a different phone, and every doctor's phone had a slightly different aspect ratio. So you could actually, basically, the phone was telling you who the doctor was. And that once you knew who the doctor was, that told you what patient population they served. So you could make a model that predicted what tissue type you were looking at just based on the aspect ratio of the image. And you don't want to do that.
Right. So
then the trick becomes, how can you split up your data into training and validation sets so that you don't overfit? Because the thing is that if you have data from Dr. A in the training set and in the validation set and in the early stopping set, the algorithm is going to keep on overfitting, and you're not going to notice, because the data from Dr. A is in the training set and it's also in the early stopping set. If you have a different doctor in the early stopping set that's not in the training set, now all of a sudden when your algorithm starts overfitting, then you'll start to perform worse on that early stopping set, and you can stop training before the algorithm overfits.
Okay, we're starting to have people drop off. Oh, sorry. Okay, we're starting to have people drop off. So thank you so much, Kiri. That was a really great presentation on a very underappreciated problem that really has a lot of depth to it too. So that was awesome to see. If I could get everybody to unmute themselves, or if Bruce, you can unmute everybody. Well, let's give Kiri a warm round of applause, a virtual round of applause, and 3, 2, 1. Awesome.